us assistance to hold such event. Okay, you can start. Thank you.
Okay, so welcome to my now last lecture for this week, unfortunately. I want to talk about movement patterns today, and let me start again with this general overview of, you could say, general purpose questions, and let's see what we talked about. We talked about simplification, we talked about segmentation, then there's finding recurrent patterns and subtrajectory similarity. We talked about similarity computations we've seen several times. Clustering, to some extent as part of clustering, finding a typical trajectory. Visualization is here on the list that I didn't talk about. And the last point here on the list that I didn't mention yet is flocking or grouping pattern detection, or more general what we call movement pattern detection. So this is from a taxonomy of movement patterns. So it's separated into behavioral patterns, so they are more kind of linked to specific behaviors like foraging or migration. And then there are these generic patterns like temporal sequences, temporal periodicity, or spatial-temporal periodicity. And all of this falls under the larger scope of movement patterns. So there are many, many movement patterns, in particular also many that describe groups in some way, that describes behaviors within a group to some extent. And the challenge is always to find a formalization, so some kind of useful definition, which is on the one side not too specialized, which is also not too abstract, so that it's actually useful for something, and for which we then at the very end also are able to actually come up with algorithms. So let me talk a bit about the problem of detecting groups. So again, this has been studied by many, many people, and there are various ways of defining groups, and I will show you a few of them. In principle, we're looking at a set of moving objects which at some time are together and then which travel for some kind of longer time together. So that is what we mean by a group. And a very early approach to detect groups is the following. So if we very strictly interpret what the groups that I showed on the previous slide, then there's a parameter which describes the group size. There's a parameter which describes how far entities may be outside of apart from each other. There's also maybe a parameter which describes the duration of groups. And if I look at these trajectories, so they're starting here, moving there, and I look at their movement over time, so at this point they're close together. And when one way, so I need, let's say my group size is 3, so these three are close together. This one is still a bit further away. So one way to describe what a group could be, at least in a very simple geometric description, is that these points should lie inside a disk, and they should remain to lie inside a disk over an extended period of time. And at this point, the group ends again. So in this case, we would detect this group over this duration. So there are several perspectives on this, and that depends on essentially. So maybe the first parameter that you have to think about is, if I'm now asking for a group of at least 3 entities, then the question is, one question is, does it always need to be the same 3 entities? So one possibility is to say, okay, as long as there's at least 3 entities moving together, then I would still call it a group. So even if, so this one is already fairly close, so even if this one would move here further away, I would still have a group of 3 entities. So, and that is a distinction between fixed subsets or variable subsets. So whether if I look at this group which exists over time, whether the group is simply where I'm saying, okay, I have this disk and there are always at least m entities, or I have this disk and there's m entities and they also stay the same. So this is this concept of a flock. You can also ask about meeting. So meet is something where the entities come into and move out, and the contrast here for a flock is that this disk is moving, and if you just want to find a meeting place, then you're looking for a stationary disk. So that is just one way to formalize groups, and I actually don't want to talk about this approach more, but just want to show you a few definitions that have been considered. So the next one would be what was called a convoy. And the idea of a convoy is to say, is essentially a type of clustering. So in the x and y are directly connected if the epsilon disks around them are overlapping, and then they are connected if they are connected if you can find a path of directly connected disks. So this is more like based on single linkage clustering. And the definition of a convoy is simply a group where everything is epsilon connected. So it's very close to single linkage clustering. Still, this is what people in GIS considered as a definition of a convoy. It's also not that ancient, the paper. I mean, it's now 10 years old, which I at least find a bit surprising, because it seems like not, if you think about what a convoy, I'm not sure what a convoy is in your mind, but in my mind a convoy is something where there are things moving and they're also moving behind each other, and to some extent, I mean, sure, there's something moving together, but this does not, in my mind, capture a convoy. So this could be a convoy if it is moving, but this, following this definition, is also a convoy. Okay. So there are many definitions, and you should always skeptically think about whether this actually formalizes what you actually wanted to formalize. So this was groups. Now I'd like to talk about leadership and following behind. So I again start with a rather old paper. So the first definition of leadership that I'm aware of is this definition where you say, okay, this one would be a leader. No, this one is following somebody. If there's somebody, if I look at this directed cone here, and there's somebody in this cone, so this is the front cone of this entity, and now this one is following the other one. And then if you want to be a leader, then you should not be following anyone else, because then that other person would be the leader. If you want to be a leader, you need followers. So in this definition, you should have at least m followers. So this could be the leader here now. Because let's see, it's in all of these cones. And then, okay, this is just at one point in time. So if you want to have a leader in terms of movement data, you want to have a leader which leads for a certain duration. And if you look at this simple definition, then I mean, essentially you can check this pairwise relation between any two entities in n squared time. Then if you have t time steps, then the number of relations you want to test is n squared times t. And then if you do it over, if you think of this again as polygonal curves, so you're doing this continuously, so then you'll have to check for events, when does something enter such a cone or not, and then you end up essentially with, you could say, you have to process events when this happens. So you have some kind of priority queue, so you get an extra log factor. And this, okay, You may or may not agree whether this captures leadership. It is from 2007, so that was a time where a lot of these movement pattern papers appeared. And I would say, looking back, or in particular, later talking to biologists, very often this leadership, I mean, it's more subtle than this. In particular, you can also lead a group from behind, for instance. This is not captured at all in here. So, but I think geometrically speaking, it is a reasonable definition. Then just one more, yet another movement pattern. So if I'm looking at popular places, so a popular place could be simply some location which is visited by many different entities. And this is a paper also by Joachim Gudmundsen. I think he actually also talked about this here when he was here. And I also won't say much about it. So what they were looking for is a region, and for instance simply a unit square, which is so it's called popular if at least m entities visited. And okay, let them have. They'll now move 1, 2, 3, 4, 5 visited. Some others visited again, I think, but 7. So there were 7 visits, but only 5 entities visiting. Exactly. So in terms of, if you talk about popularity, you're not counting visits, but the entities. So this would be popular with m is 5. We actually recently looked at this algorithm again in a setting where we want to compute it, where we want to compute popular regions, not in one go, but more in an interactive setting or kind of a progressive setting. So algorithmically, so if you think this is an interesting problem, I think there's still a little bit to do there. If you look at different objects you want to compute, or different constraints that you put onto your computation. Now, one more. No, I have two more topics which are both a bit bigger. This is the first one is single file. So this was actually, I think, the first paper where I actually my first paper on movement patterns. So I'll have to show it. Even if Joachim also showed a little bit of it, but I have some extra slides. And my extra slide, so our motivation then was single file. So single file means I have this penguin and it's moving, and this penguin is moving behind this one behind that one, and so on. But to some extent, if you look at it pairwise, you can also see it simply as a delay. Somebody is moving and somebody else is moving a bit later, and that is kind of the perspective that we took later. So let's have just a few examples of what we think would constitute single file movement, or if I just have two movements, two entities, a movement with a delay. So these two, let's have a move. So delay or not, I'd say yes. I mean, the delay maybe was a bit large, but it was still similar movement. So huge delay. So in terms of delay, yes. In terms of single file, part of a single file, I would say no. And at some point, I mean, and the point of this example was at some point it's just two entities that at some different point of time moved on the same road, so that it's not really an interaction between those two entities. So the movement with delay, it's not really single file, so it's somewhere in between. So what we in principle want to capture with a single file movement is that I have one entity that's leading, another entity that's following the leading entity, a third one that follows the second one, and so on. So and as such, it can be described by pairwise relations. Yeah, so this is what I ideally want to have as single file. And if I look at it as a pairwise relation, then it's a property, you could describe it as following behind or delay. And now let me do this example once more. So this one is following that one. And so here they started here and now they're here. And one interpretation of following behind is to say that the second entity is now at least more or less where the first entity was previously and not too far in the past. So if we take this perspective, we can say, okay, this entity should visit maybe an epsilon disk of where that entity was previously. And to make it really delay, there should be at least some delay, and to make it not to have at least some kind of relation between the two movements, I also might want to impose a maximum delay. And if I then formalize this, I might end up with the following. So I have entities x1 and x2. They have they move on parameterized trajectories f1 and s2 over some time intervals. And then what I want to have is that s2 moves, so s2 should be, so the starting time of f2 should be delayed relative to s1, and the end time of x2 should be delayed relative to end time of the first entity. And now the one entity is following behind the other one. If I can essentially I can find a reparameterization such that this reparameterization only changes time or changes time by at least t min and at most t max, and after that reparameterization those two trajectories should be close together. So what this means is I have the two entities, they're moving. So if I set this one, you could say change the time of this one by the time it needed to move to here, then it exactly or nearly exactly is the same trajectory as the other one, or is at least a very similar trajectory. So here once more, this is the one trajectory, another one, and let's have them move. So this one moves first, this one moves behind. And if I now slightly reparameterize the second one, I can let them move together. Which, let's have a look at this in once more in terms of, so this is now space and time. So what this means in space and time is I have my first trajectory f1 and I have my second trajectory f2, and then if I shift f2 in time, then it becomes, and shifting in time you can think also of kind of, so f1 allows some kind of cylinder, so in terms of, so you have the epsilon disk which is the space, and then time gives you some kind of cylinder, and then f2 will pass through the cylinder delayed relative to f1. Okay, and all of this smells like Fouché distance, which I already talked about several times. So essentially in terms of Fouché distance, what this means is I want to compute such a reparameterization, but the reparameterization of f2 should express the delay of f2 relative to f1, which means that, so if you look at the alignment along the diagonal, then it would mean you just take the times as they're given. If you look at an off-diagonal alignment, then it means you're taking the time with where one is delayed to the other one. So, and that is how how we model this. And then if you look at the running time, in principle it is, you have this quadratic free space, but if you take into account that you're now just looking at a thin strip of the free space, then you can look at, then essentially the running time goes down, because you will always only have to look at a constant number of at a small number of cells per row or column. So that is expressed by k, the number of cells that fits into such a diagonal strip. T is here the number of timestamps. You get a running time of k times t to check whether a parameterization is correct. And then if you want to kind of test over the whole trajectories, you can build, essentially this is similar to the data structure which I showed for the subtrajectory clustering, just that you have now very narrow strips, and then this running time is linear times k squared, where k squared expresses how much on average in terms of cells you have within such a strip. So this is by now a somewhat older paper, but we actually recently needed the techniques again, and then so we also then implemented it, because there we were interested in for animal movement. We wanted to know who's leading or who's following, so who's initializing some movement and who's then kind of reacting to that. And there we simply, so this is an approach from the older paper implemented. What you see here, this is now not the free space but the distance matrix colored. So when it's very dark, it means that it's very close, and the red parts are very far. Then we compute an optimal path in the distance matrix, and you can choose whether you want to use discrete Fouché distance or dynamic time warping or other optimization criteria. And what we use this now for is not to detect single file as such or following as such, but we now take the optimal path, no matter whether it falls into a strip or not, and from that just want to learn how the animals or objects related to each other, in the sense that if the optimal path is close to on the diagonal, it seems that they simply move together. But if it's off diagonal, like here, then you can assume that the second entity here reacted to the movement of the first one. I have 2 more slides on this. So this is Euclidean distance. But since you yesterday asked me about distance measures that combine direction and distance, so this is the setting where we use that, because here with you I didn't mean everyone, but Professor Buchin and the student. What was the student of you who asked? Yes, exactly. So this is the setting where I use this, and the source code for this is also available. So this is here. So this is an example where instead of dynamic time warping or discrete Fouché distance, we used a combination of distance and direction, so weighted distance, and then computed the path, and then used this to look at delay. And so this is a delay plot, and that is a distance plot. And let me just show kind of a more schematic representation of this. So what we often see in these plots is something like this. So the dotted line is the delay. So what you see, we're starting here with, so one of the entities first has a delay, then they're essentially nicely aligned, so then they fly together or run together, whatever they're doing right now. And now the delay increases again, and then it decreases. And in terms of the black line is the distance. So here we have a large distance. The distance goes down to nearly 0. It makes a big jump, and then it goes down slightly again. And if we see this kind of pattern, we interpret it as a action-reaction pattern where the one entity initializes some behavior, the other one doesn't immediately react, so that's why the distance increases suddenly, and then also the delay increases, and after that action, the second entity adjusts, so then the delay also decreases and the distance decreases again. So we used that to look at action-reaction patterns between bats. So
in fact, the delay diagram could be recovered from the distance diagram, isn't it?
there is obviously a correlation, but it could not immediately. So I would say no, because there is typically the strong correlation, but if you know the distance, you don't know who's leading, who's following. You could also have a setting where somebody, so this is following, nice distance, and now this one overtakes. So then the distance would always stay the same, but the delay would switch from this one is delayed relative to that one to a case where the other one is delayed relative to the other one. Yeah, so it's not, there's no one-to-one correspondence, but I think the combination of both tells you quite a bit about the what is happening in terms of the interaction between the objects. So here I'm back to this overview, and I showed you a couple of examples, and where I'd like to go next is something that we call a grouping structure. So where I showed you several definitions of what a group is, but what we wanted to capture here is how over time the groups change. So we didn't want to simply detect groups, but we wanted to somehow describe how groups change, whether they split, whether they merge. So what we wanted to capture is we have moving entities, they're forming groups, and these groups might be merging and splitting, and we somehow want to have a structure that defines and computes that, so which means that we first need a formalization and then an algorithm. Again, we were not the first to consider that, so there's various ways to describe groups. So flocks I already described, convoys, herds, swarms. I'm not sure why people always have to come up with new names, in particular if they don't match, but okay. Moving groups cluster, that's at least somewhat generic. So what we want to describe is what over time how groups evolve or split. And what was important to us was that we wanted to use the whole trajectories instead of simply the data points. So instead of looking at the discrete problem, we wanted to look at the continuous problem. And we wanted to look at the overall structure over time and not just kind of finding groups at certain moments in time. And we were aiming at some kind of mathematically clean model, and then obviously at some algorithms. I will also show you at the end some results from the implementation. So let's look at moving points again. So this looks like a group, this looks like a group, I would say. But now they move over time. So now we can wonder, was there a group here or not? That kind of depends on your perspective. Was there a group? What do you say? Huh? You say no? Yes, you say no. Huh?
This 5 points you can define same problem and so on.
Yes. Okay, so that could have been a group, but a very short-lived group. This now slightly more looked like a group. And what I want to demonstrate here was, okay, obviously there is some kind of spatial distance which is important for the groups. Also, you have to have enough entities. But then a possible parameter that is important is how long does this group actually exist. So those were the three parameters that we used: group size, distance, and duration. Then also, if you don't want to kind of detect just a group at a certain moment in time, but want to look at all groups, then you have to be a bit careful. And we said we are only interested in the maximal groups, because obviously, if you have if I set my parameter for group size to 4, and I have 8 groups moving together, 8 entities moving together, then a structure that somehow reports all subgroups of those 8, so 8 choose 4 groups, is not really a nice representation. So that means we wanted to have maximal groups, and maximal in the sense of group size, so which means that it's not possible for this group, given those 3 numbers, to kind of add a member and then still be a group over at least the same time interval, but also maximal in terms of time, so in terms of duration, and that means in particular instead of start time and end time. So we're not interested in a group that, let's say, of 3 entities where the same 3 entities also move together actually for a longer amount of time, because then we could have immediately take the longer amount of time. So that's what I mean by maximal groups.
So if you have the setting, is it static or dynamic? I mean, if somebody can join and then somebody leave?
So here, yes. So that is a setting where we would see this as several different groups. So just to, since you now asked the question, it will come later also, but if I have, so if these two, I tricked myself. This one is okay. Let's see. This one, okay. Let's see where this one is blue. Yes. That's also blue. My apologies. One of these has to be black. So some kind of pigeonhole principle should apply. It's always the last one, huh? With a blue cap. This is black. Fantastic. So, the way we want to interpret this setting is, let's say M is 2. So groups should have at least size 2. My distance is, you can assume what my distance is. So then I have these two start moving together, and they move together up to here. And we would see this as a group, and it's also a maximal group, because I cannot not extend it into the future. I cannot extend it backwards. And if I would extend it in terms of size, so I add this one, then it also becomes shorter. So this is another group, and then there's a third group here.
So we count them separately.
We count them separately, and then we want to nicely represent this somehow.
Somehow, isn't it somehow the concept of clustering the software usually?
It is, to some extent, yes. It's a bit different from how I described clustering subtrajectories, in the sense that in the previous settings I always looked at trajectories that are not aligned in time, so I was more clustering their path. Otherwise, it's not really clustering in the sense that it's partitioning, but it's more like clusters, subtrajectory clusters. Yes. Yes.
In the criteria, you mean the number of time steps or only the duration?
Number of time, I mean duration in time.
Then we don't ignore this feature.
The speed doesn't directly,
Is included.
the speed is not included. So I mean here it is about time, not about length, you could say. That means that if they're moving, yes?
Can we say that it's the number of time steps there?
You could say it as a number of time steps. The reason I wouldn't call it the number of time steps is because we're looking at this continuously. So it's the duration. But in the discrete setting, it's simply the number of time steps, yes. And what this essentially boils down to is looking at the connected components of the moving disks, where I said the disk radius to d half. So let's do that. So these are my points, and then what I want to have. Okay, I should have said so close enough. This is interdistance smaller equal d. So by this I again mean a kind of single linkage setting. So and that means that here I'm looking at the connected components, because now if this is a disk of d half, these have distance d and form a connected components. This is at time 0. And right now if m is 2, let's say, I would have one group. Now I have a different group, and intermediately had yet another group. Okay, so if you look carefully, we had events at these points in time. So let's try that again, knowing that there are events. At point here, the red one joins at time 4. One of them leaves. Let's see. One joins at time 4. Which one was leaving at time 4? Let me do that once more. One joins. And here, at least, here those two join again, and this is simply the end. And here one was splitting off, the other one was splitting off. So if I now look at maximal groups, and now assuming I need two entities and duration 3, then the groups that I would get would be green blue over the time 0, 4, green blue red over 1 to 4, then at time 4 green left, so then I had blue and red actually existed over 1, 5, time from 1 to 5, and green and purple from 8 to 10. But if I then look at maximal groups, let's say for m equals 3, then I would only have this one group. And if I instead say I would like a different parameter for delta, so they should exist at least over 4 time steps, then you get green and blue and red as groups. So kind of a visual representation, illustration of this is the following. Let me actually go immediately to the next slide. So the 2 dimensions here, in terms of the groups that we would like to see, are here I'm looking at the size of the groups, and here at the duration. And depending on how I set parameters, maybe I only get, so this is the example where I need at least 5 entities over a fairly long amount of time. If my duration, if I set it to smaller, then I would get those groups, and so on. So depending on how I set my different parameters, I get different groups, and here the coloring now expresses how large these groups are. So, but this is not yet a kind of nice and clean structure. And to define the structure that I'd like to use, I want to do a short excursion to topology, a very short one. So I assume quite a few of you know computational topology, maybe even better than I do. But let me just kind of briefly show you a few things. So here it's more, so in the structure, so the structure that we want to have here will be more about, you could say, connectivity. So because we had these disks, so and we're looking at connected components in terms of these disks. So we can abstract away the geometry, and that is a setting where we can nicely use topology. If we're more interested in structure and connectivity than the specific geometry. So computational topology is a beautiful field of itself. Jeff Erickson also talked 2 years ago about topology. So as I said, you know probably more than I do. It has many applications. Let me actually then simply jump immediately. Let me just skip this slide because I think most of you know computational topology. I just jump immediately to the structure I want to talk about. Not here yet? No. Because I want to talk about the weep graph. So the weep graph, for the weep graph, you'll need Morse theory. So we have the space. We have some function defined over the surface. We have a function defined over the surface, and in Morse theory we will look at the critical points of this function. And critical points means that the gradient on the surface is 0, and the index of a critical point describes essentially how many in how many directions, or in how many principal directions it is decreasing. So by an example, and already closer to what we actually want to use. So if this is your surface, so you have the surface of you have a torus. If f, your Morse function is height, then you essentially look at how the connected components change while the height changes. I think it's really easier to describe with this example, so let me just show you this slide anyway. So think of this torus, which you put into your coffee, and look at the part that is now below the surface of your coffee. Then if you just dipped it in, you just have this very small part, and that is just one simple surface. And now if you dip it in until it hits this point here, and in terms of the Morse function this is a critical point, then suddenly this closes, so you get a hole in your donut. Okay, probably your donut normally is not is filled inside. This one is not. So then, if you just look at the surface, now there's a hole. So just before there was no hole; it was just a simple surface. Now we have a hole. So that was one critical point. The next critical point is down here. So if I dip it in more, then I don't only have this hole here, but I also have this hole in the middle. So again, the topology of the space changes. And the last critical point is if your donut is gone. Unfortunately, it's gone then, and then it closes. Okay, and this is then this example where I have a minimum, a saddle point, a maximum. So that are Morse functions and the critical points, and where they show up are how you can capture or have a schematic way of representing this function is a weep graph. So here you have a vertex for every critical point, and then you have edges for connected components. So if you think of your coffee, I'm thinking of my tea. If you think about your coffee, then and the donut, then here between those two critical points there was just one component. Then here, if you just look at the slice, so don't think of your whole donut, just look at that slice here, then you have two components, and then again one component. And this is then the weep graph that you get. And okay, why did I tell you about weep graphs? Because this is exactly the perfect structure to represent the groups that we wanted to show.
So, your events will be joining and leaving?
Exactly.
And then you start to change the group to two or merge them to one group and then...
Exactly. So, you know everything else now. Now you can get your sleep.
I'm going to sleep.
Okay, so we're going to use a weave graph. Edges are connected component. Vertices express when there's a change in terms of connected components. So here I had one big component. The green point moving object split off. So in terms of, if you think of this now, think of this as a surface in time. Then and the slices. Then you had one component and moved to two components. So that would then in a weave graph correspond to, this will be a critical point of the function. So a vertex here, and I have one component, two components. So a split. So more examples. This is again the example that we had previously. And the corresponding graph that we would like to get is then this one, where every vertex corresponds to a change. And now I will want to label edges. So let's say, right now I say M is 1, which is not really a big group. Everyone is a group. Duration is 0, so this is kind of the kind of most, the weakest version of what a group could be. And then I can start labeling these edges with information of which group this edge might correspond to. So during this edge we had this red, blue, green group. Or here this was just green, and so on. And here are the timestamps. So to show the connection to topology better, as I said, it's good to look at this time axis as an additional dimension. And then these epsilon disks, they give these tubes. And then it's really about critical points of the height function on this surface. So, and you see, for instance, here x1 and x2 were separated. Here they join, so then I get this gives me a critical point where two components join, and so on. So let me start by mentioning the results that we get. So if I have t time steps and n entities, then, and I'm assuming piecewise linear trajectories, then this weave graph will have size t times n squared. So in the worst case, it's actually quite big, and we can compute it in essentially in its size with an extra log factor. And there are essentially four types of vertices. We have start vertices, end vertices, merge vertices, and split vertices. And we can also look at them in terms of their degrees. So the in and out degree exactly tells us whether it's a start, end, merge, or split vertex. So in terms of the complexity, so why could the complexity be so high? If I look at, so this is now between here, this is the location of the trajectories at one time step. This is a location at the next time step. And now if they're moving, obviously I can get many different small groups that, or you connect a component that just briefly exists and then disappear again. And I could have this during every time step, and that's why I can have a weave graph that has at least the size of t times n squared. And arguably this is really a very worst case, because hopefully between time steps not so much happens. But okay, on the other hand, it could be fairly complex, because if they're moving closely, you can also have a lot of interaction. So this gives me n squared in one time step, so t times n squared overall. We can also see that the weak graph, so that was a lower bound. I mean, I gave you an example of t times n squared. So we can also see that t times n squared is also an upper bound. And the reason for that is if I look at two entities, then those two entities between one time stamp can also just generate one vertex of the weak graph. Because we assume linear motion, so they can only once come very close and after that move apart, and it won't happen that. So two entities as such cannot during one time step come close several times. And that gives me n squared components per time step, so overall I get t times n squared. Now, to compute this, essentially you can think of this with the cylinders, and now we're doing a sweep over time. For that we first find all of the events. We sort these events according to time and then put them into a priority queue. And to make this then work, so we initialize the graph. To make that then work, we need some kind of, we can use any data structure that is able to keep track of sets under unions and splits. So we use here ST trees, and then we get this log n factor. Now I have, how much time do I left? No, I can. If you don't stop me, I will continue forever. And if you stop me, I can wrap up nicely.
You know, a quarter or maybe a little more you want, or less.
Okay, but I started an hour ago, nearly, no?
5-10 minutes.
So I'll do more like 5 minutes. I'll make sure to wrap up. I'll just give you some ideas of what's still to be said here, and then because I also want to at the end have time to talk about, to wrap things up. So what now could still blow up in terms of complexity is the number of maximal groups, because we now have this weak graph which expresses merges and splits, but that does not yet tell us how many maximal groups we actually have. Because, I mean, for this edge, I know, okay, there was red, blue, and green moving together, but an edge as such is not yet a maximal group, because this red, let's say blue, green, this group existed from here, blue, green, ended here. So there's not a correspondence between edges and groups, and there can be many more groups than we have, than the size of the weak graph. So in the worst case, we have t times n squared maximal groups. And let me just give you the idea of the proof. So this is the size of the weak graph in the worst case, t times n squared. Then we need to prove that at any start vertex or any merge vertex, at most n groups start. Because, okay, at an end vertex, there's no group starting. And at a split vertex, where's a split vertex? A split vertex, there's also no group starting. Because anything, after a split vertex, there might be still groups existing, but those groups must already existed before the split. So it's really just the merge vertices and the start vertices where you could get new groups. So in our example here, we had one group starting at the start, and two groups actually starting at the merge vertex. So it can also be several groups starting there. But I'm arguing that at any such vertex, at most a linear number of groups start. And let me just do this by this illustration. So this is my weak graph. The way we do the analysis is essentially that we now cut open at split and merge vertices, because if I now want to count how many groups, so I want to now start how many groups start at V, and that right now is still difficult to read off, because okay, let's say there was a group going here and one going here, but then both of these might exist after this merge vertex. So if I just look at end vertices, I can as such not count how many of these, how many vertices, how many groups started from here and ended there. But if I now cut this open, so what you see here, let me do it. I cut it open at any merge and any split vertex. Then eventually I get a one-to-one course, not a one-to-one. So then at any end vertex after this cutting open, there can be at most one group that started here and actually ended there. And likewise for any split vertex the same. Now for this vertex I just have to count how many end and split vertices there might be. It was previously essentially looking it up. I mean, we could at least have at most an outer degree of 2 at any split vertex. We have a linear number of split vertices. So the number of cuttings here is overall linear. So overall the number of vertices where I could now end from V is still linear. And that is essentially the proof that the number of maximal groups starting at V is linear. So then overall the number of maximal groups is the number of merge and start vertices times n, and that, so let me move there. That then gives me the order T times n cubed. Let me yeah, I'd like to show you once how this looks like in terms. Oh, I'll just open to not take too much time. Let me just open, show you. So this is on Frank Stahl's webpage, and there are lots of nice videos of when you set parameters differently, how the groups, what kind of groups you get and how they evolve. You can also, so we're using here a flocking model from NetLogo, and there's also we also use this data of Starkey data, so that is deer and in a kind of deer and 2 other kinds of animals. Yeah, so it's nice to see how these groups evolve, but to not go too much over time, I like to just mention it and now go back to my presentation. And I'd like to simply wrap up. Sorry. Okay, so that's just the wrap-up slide for the grouping structure. So we think it's a nice and clean model. I mean, based on topology. It's also efficiently computable. What I didn't show you is we can also make it more robust, because if you sometimes just an entity leaves a group for a short amount of time and then we still want to see it as a big group. And in terms of our experiments, it seemed to work well as a model. I talked about movement patterns today, but let's go once more back to this overall slide of analysis tasks. So I think, except for questions of visualization, which are not so algorithmic, we've covered all of this in this week. And with that, I'd like to wrap up. Thank you for hosting. So before I came here, when I was asked by Ali Mohales whether I should come, I asked Mike, who was 2 years ago here, whether I should come, and she said, "Don't think about it, you have to go." And I asked Mark, and he also said, "Don't think about it, you have to go." And okay, I didn't ask too many other questions. I believe them, so I was wondering what they meant, but I had to go. But now, after a week here with you, I would also tell anyone, don't think about it, you have to go. So thank you very much for hosting. I really enjoyed it.
that we were with Buchin family. Maybe, yeah, give them ovation. Dr. Buchin together. Yeah. You know, when our school is over, that this is our honor that for the 11th time we got together. And you know, we hope that this event caused a scientific research in communication among all the participants of this event. And you know, keep in touch with us with our via our website. And you know, that's all for me. We hope that next year we can get together again. Thank you.